Okay, so either the gizmo was confusing or maybe the worksheet was confusing. But let's go over this now. So if you look at what wavelength depends on, that has a formula that we went over in the notes. So lambda is V over F. V stands for wave speed. So this question is yes, it depends on wave speed. And then F is frequency. So it definitely depends on frequency. And then if you look down here, number 2, wave speed should have in the gizmo changed depending on the medium. So then if the wavelength depends on the wave speed and the wave speed depends on the medium, then sure enough, the wavelength should have changed when you changed the medium. And remember, what am I talking about when I talk about medium? Okay, let's switch screens and look at the gizmo itself. So when I'm talking about the medium, I'm talking about tension and density, the spring itself. Okay, because the spring is the medium through which the wave is traveling, the stuff that the wave is traveling through. In this case, we're looking at like the side view of a slinky or a spring. So then if we change something about the spring, how tight they're holding it or how heavy the spring is, then we are changing the spring, okay? And so then we are changing the medium. And you should have seen the wavelength change. Now, how was I measuring the wavelength? I was measuring it from like crest to crest, right? So that would have been on my graph. If I'm looking at the crest, I see it at 50. And then I see the next crest at about like 275 or something like that. So it would be 275 minus 50 makes 225-ish. Okay, so that's what you should have been measuring for wavelength to see if that changed. And then for wave speed, it's this number right here. So that only should have changed when you changed tension and density. It didn't change with frequency. It didn't change with amplitude. That's wave speed I'm talking about. Okay, nothing changed with amplitude. Amplitude didn't change a darn thing. Okay, all right. So then let's go back to this. And then you just measured the amplitude for wavelength, I'm sorry, for number 3. That seemed okay. And then this is checking, okay, that you understand how those characteristics change. So if you're doing what the gizmo is doing, shaking the spring back and forth, can the speed of the waves in the spring be changed if the spring has constant tension and density? Nope. Because the only way the speed of the waves, we're talking about the speed of one wave down the spring, right? Okay. Kind of like the speed of the wave around the stadium at a Badger game. Okay. Once the person's doing the shaking, but they don't have control over how long it takes a pulse to get down to the end of the spring. They don't have control over that. So no, they cannot change that. That depends on the spring itself, the tension and the density. Can the frequency be changed? Well, only by how quickly that person is shaking their hand back and forth or up and down, right? So going back to the gizmo here, I'm not sure how well this will play for you, but how, they're controlling their shaking frequency. If I now make that bigger, then I should see that that person is shaking their hand up and down more often. That is the only way to change the frequency of the waves, okay, is at the source. That has to change at the source, and then after that, it never changes. Okay. So, and then the math part, this part was fine, the speed of the water waves. On part B, be careful because they gave you period, but in our formula, we have frequency. So you have to use the period to solve for the frequency. It's only a little bit different because 1 divided by 1.1 is 0.91. So then you should get 2. You should not be getting like 1.7, 1.6, 2 or 2.1. Okay, and then for number 14, most people got 1,500. Good job on part A. Part B and C, that's a trick question. Oh my gosh, that's so rude. Okay, but period and frequency don't depend on water versus air. Who cares? Okay, period and frequency don't depend on the medium. Water and air are media. Okay, that's what the wave is traveling through. Don't care. Um, so all you have to do is do 1 divided by the frequency to get the period. Be careful. I bet when you did this on your calculator, you got a negative exponent. Just remember to check for that and copy it down. Okay. So you should have gotten the same, you just write down the same number. Okay. All right, so today's topic is sound, and we're gonna just hit the basics, okay? And you maybe learned this in middle school, but let me pause now and go to our PowerPoint for today. Okay, before we get too far on sound, I just wanted to show you I have 2 tuning forks I brought home from school. So this one's marked 440, that's hertz. So that means it vibrates when you hit it at a natural frequency of 440 times a second. And then this one is marked with 523.2, and then so that's in hertz as well. This is an A, this is a C. These were originally made to be used to tune pianos, okay? So we use these though because they just vibrate at 1 frequency only. And so they're great for physics experiments. So when they shake so frequently you can't really notice them shaking, but you can hear them with that nice pure tone. So I'm going to try to hit them on my shoe and play them for you. And then okay. So you can tell that the vibration makes sound, and that's what we're talking about today. Okay, so we are going straight into chapter 15 and just doing the first section, not even all of it, okay? So if you think about what really is a sound wave, it is just a pressure wave. So anything that shakes back and forth makes a vibration, and it creates a little pressure wave. So if you know, a classic example is a cymbal. That seems like a really noisy thing, and that is making a vibration, and it's creating a high pressure area and a low pressure area as it goes back and forth. And I encourage you to open the PowerPoint on my DSHA and watch the slow-mo video. And watch these little GIFs here. So that sound wave is technically a longitudinal mechanical wave, okay? So it's not a transverse wave. It's just a pressure wave. We call it mechanical because it is stuff. It's made out of matter. You have to have matter present for that wave to travel. And then it's traveling out through space as a longitudinal wave. Its frequency depends on how many oscillations per second, oscillations of pressure there are. And then the speed of sound is dependent on, again, like we said, for all waves, it depends on the media it's traveling through. For air, that depends on temperature and humidity. And it happens that sound travels faster in liquids and solids than in gases. One anecdote is that, you know, I guess I've heard that elephants can sort of sense a stampede of another animal, or they can sense like an earthquake vibration through their feet, much earlier than like other animals could hear it through their ears, because they have sensitive pads in their feet, And of course, the wave is traveling through the ground, which is a solid, faster than it's traveling through the air as a gas. And you can see some of this on this chart. You can see how much faster those speeds are in liquids and solids. Okay, and then like we said, because sound is a mechanical wave, it has to have stuff to travel through, which means it cannot travel through empty space, which we would call a vacuum. I put this picture in there because I'm pretty sure that in Star Wars they had a sound effect to go with this scene. But if you're viewing from outside, of course, you're dead. You're dead if you're in the explosion, right? So if you're viewing this from outside, you wouldn't hear it because there would be no sound in outer space where there is no air. So it would just be silence. Okay, but I'm pretty sure they put some kind of explosion noise with it because it sounds, I mean, wouldn't it be anticlimactic to not have a sound to go with that? Anyway, okay. Now, what we would call the frequency of the sound, your ear picks that up, and we call that, in music, we call that pitch. So you hear a higher frequency sound wave as a higher note. Amplitude is associated with loudness or volume, which makes sense. And then humans are good at hearing. I mean, not as good as other animals, but we are pretty good at it. We could hear, a wide range of noises. And so we have to use a log scale to represent all the possible noises that we can hear, from very quiet to very loud. And so this decibel scale that we use is a log scale, kind of like the earthquake scale is also a log scale. So 10 decibels is hundreds of times quieter than a whisper. Okay, this barely audible is hundreds of times quieter than a whisper, which is hundreds of times quieter than a casual conversation. And so even though like alarm clock looks only mildly quieter than a siren, that's not actually true, okay, because it is a log scale. Okay, so I'm gonna stop there for today. Our next lesson on Wednesday is actually going to be not about sound, but about the other important kind of waves, which is electromagnetic waves. So please go do the assignment on my DSHA, which is checking that you can try those math problems again, okay, and understand what variables depend on which other variables, so that we'll be ready for a test next week in finals week. So please reach out to me if you're confused, so that you're not confused in the future. Okay, thanks, girls.